Yeah, Venkatesh. So you are the host now.
Okay, so yesterday we have seen how to means we have gone through that load flow reports, how to go through that reports, and we have discussed about the study cases and the scenario wizards and the study wizards also. We have seen means in a single click if you want to run the set of load flows. So how we have to use the study wizard. So with the help of the study wizard, we can perform all the studies. Means we can perform we can run all the study cases in a single click shot. So that's what we have seen yesterday. And today I'm going to discuss the last topic for the load flow, that is OLTC, means the on-load tap changer. So for that, let me share my screen first. Yes, right, fine. So today we will see how to select the on-load tap changer, especially the de-energized tap changers, how to select the voltage range. Okay. And with that, just try to have, we have two options for selecting the OLTC or the de-energized tap changers, whatever it may be. So generally two type of tap changes. One is OCTC, or we will call it as a de-energized tap changer. That means you can change the tap only when the transformer is in the off condition. And the second one is the OLTC. So this is called the on-load tap changer. That means even when the transformer is in service, you can, even though the transformer is in service, you can change the tap from one point to another point. So there are two types of tap changers. Okay. So here, when we are optimizing the transfer or tap changes for the transformers, we have to see in the two perspectives. That means one may be from the load perspective, and the second one may be the source perspective, or you will say it as a perspective. Yeah. So now let us have a selection of OLTC. Now probably we can do the questioning like, when do we need OLTC? When we will be okay with the de-energized tap changer and all. So first let me ask one question. Where do we need OLTC? Any answers? Where do we need OLTC?
For a voltage control, sir. Voltage variation.
Okay. So we can say like to regulate the
Voltage level, sir.
transformer output voltage with the different load voltage fluctuations, right?
Yes.
Yeah. So where do we need OLTC? Conventionally, by default, we generally think that OLTC is just to regulate the voltage, but the reality is a little bit different. If you have like an arc furnace, let's suppose if you have loads like arc furnace, or you have the traction loads. Okay. So if you have a sudden change in loads, so definitely there will be a change in the voltage. And probably that time the on-load tap changer is not really an ideal device to regulate the voltage there, right? So OLTC is a ideal device for a voltage regulation only for the steady state voltage fluctuations. Steady state voltage fluctuations. So what that means? By season or probably day to night, if there is a change in load and because of that there is a change in voltage, then probably the on-load tap changer is a good device to regulate the voltage. But if you take the cases like arc furnace or for the traction applications, where there is a sudden change in load, right, which suddenly comes and goes out. So in such cases, this OLTC cannot work at all, because OLTC is not for the dynamic voltage relation. OLTC is for the to maintain the voltage within the limits for the steady state voltage fluctuations. So for these type of applications, these are all means these will what is it, for this you need a separate type of control devices, voltage control devices. Whereas as far as the OLTC is concerned, so generally these are like a type of devices. These are like a static voltage regulation devices, which means in this OLTC, you are an AVR which measures continuously the voltage, and if the voltage is consistently, let's say below, say that for example 95%, and let's say for more than, let's suppose for 3 minutes or 5 minutes, whatever it may be, then you can take an action to change the tap from one tap to another tap. And even changing the tap from one position to another position, it takes few seconds. And when it settles down in another position, then it will boost the voltage, right? But when you see the applications of this arc furnace or the traction applications, so there the load is very much dynamic. Much before you initiate the change in tap, that means if you much before you give the command for the tap change and achieving that, so by the time that load might have come back to its normal value. So where there is no voltage, and if we have changed the tap, that results probably in the over voltages in the case of the arc furnace in the traction applications. So in these applications, OLTC is not really an alternate. It is not an alternate for this devices like SVC or STATCOM or any other fax devices to regulate the voltage. So we need to understand what are the devices that are available to regulate the voltage. We need to understand what is the range at which they can regulate the voltage. Okay, is it like plus or minus 30% or plus or minus 5%? Okay, is it like plus or minus 30% or plus or minus 10% or plus or minus 5%? Okay. So also we need to know what is the response time, whether it is in the milliseconds or microseconds, or is it in few seconds, or the OLTC will operate in a few minutes, etc., etc. So OLTC range probably comes with the time delay. If you have scenarios like sudden fluctuations in the voltage due to maybe some cloud event in a solar plant, or probably the applications of the arc furnace, sudden traction pickup loads, etc., there this OLTC will not be able to help. Okay. I hope this is clear.
Yes, sir, clear.
Right. Now, so when we are talking about the OLTC, now the next question comes is you need to decide where to go for OLTC, where to go for OCTC or de-energized tap changer. Okay. And we need to also understand the fact that near about 25% of the transformer failures happening in the power transformers are due to the tap changer only. That means almost 1/4 of any failure which is occurring in the power transformer is because of this on-load tap changer. Why it is so? Why the 25% of the transformer failures are happening due to the on-load tap changes only? Why it is so?
Because of the moving, sir, at load conditions. Because the tap changing at a time, the conducting part.
Malfunction of the tap motor.
Yes. Because the only movable part in the transformer is this on-load tap changer. So obviously the failure rate is also more, which is essentially to know. Even if you have an on-load tap changer, still it is not advisable to keep changing the tap quite frequently. Okay. Typically like 10,000 operations. So if you see the data sheet of any tap changer, they maybe give the life of the tap changer will be like something like 10,000 operations, which means even if you are doing the tap change once in a day, so that means 365 days. Yes. So for almost near about 30 years, you need to probably change the OLTC cubicle. So what I mean is every day, one day, if you do one operation of the OLTC, so for 365 days, you will be doing obviously 365 operations, and that is the number of operations in a year. So for 10 years, obviously it will be 3650, correct?
Yes, sir.
3650, then 30 years you can do that. And typically the transformer life is also in the range of this range only 30 to 40 years. And if you are doing more number of operations, then it is much before the life. You need to probably do something for replacement of this on-load tap changer. Okay. Now the next question comes, where this OLTC is needed. Means my question is needed. Means my question is it required for a power plant? or is it for a load center? Okay, so where this OLTC is needed? Any answers? Is it required for the power plant or is it required for the load center?
Load center, sir.
Load centers.
Okay. Any other answers I can expect? Okay, right. So it is for both the applications, means it is for the load center as well as it is for the power plant applications both. Let's why? Because in the load center, of course, that is clear. Everyone knows about that. The load center, there the VOLTC is needed to maintain the voltage at the load bus within the permissible limits. That's pretty much clear to everyone. But what is the purpose of this VOLTC or the OCTC in the power plant applications? There, especially if you take the system, the VOLTC is needed just to make sure that the entire generator capability can be extracted. Just to extract the entire generator capability, this OLTC or the OCTC is needed in the power plant. Okay, because in the power plant, it will be something like you have a generator and you have a generator transformer. So that through the generator transformer, it is connected to the grid. So if you want to extract the maximum capability of the generator, then this OLTC or the OCTC is needed for the power plant applications. Okay.
But sir, how, sir? You tell, but how to not understand, sir, this.
So if you see here, so this is your generator and this generator is connected to, let's suppose, because the generator voltage will not be high voltage, it will be something like, suppose if you take a typical 800 megawatt generator, it will be something like this, 800 megawatt, 27 kV, right?
Yes,
And
sir.
the generator, there is a generator step-up transformer which increase the voltage, which step up the voltage from 27 to, let's suppose, 420 kV volt. And from here, it will be connected to the grid. Yes, and from here, it will be connected to the 400 kV grid, something like that. So here, if you see here, so this is your LV side, right? This is your LV and this is your HV. And all of us knows that the taps will be on the HV side of the transformer. There are so many reasons for that. So generally the taps will be provided on the HV side of the transformer. So now if you see here, so here if you say the purpose of this OLTC or the OCTC in the transformer is to regulate the 400 kV output voltage, the answer is no. Because just with this we cannot able to maintain the 400 kV voltage. But here the purpose is your generator is having the capability, right? If you see the capability curve of the generator, it will be something
Okay,
like
yes.
this.
Yes, sir.
Okay, it will be something like this. So here, the purpose of giving the OLTC or OCTC is to extract the reactive power, complete reactive power that is available in the generator and to send it to the grid or to absorb the amount of reactive power as per the capability limit of the generator. So just to ensure that in this generator step-up transformer, we will provide the OLTC, but not to regulate the voltage at the 400 kV bus. Okay.
Okay, sir.
Yes, I hope this is clear. Right. Now, just to understand how to do the OLTC. So for that, just let us pick up a small application for the load center. So let's assume that we are having a 110 kV by, we have a 110 kV utility system and we have a transformer that is a 110 by 11 kV transformer. Okay, assume that this 110 kV is a grid. On the obviously the grid, there is a voltage fluctuation. Assume that the grid is very weak. So the voltage fluctuates from, let's suppose, varies from plus 12.5% to minus 17.5%. Assuming that this is a very weak grid system. Okay. 12.5% plus 12.5% to minus 17.5%. Also assume that we have a load let's suppose the load variation will be something like 10 megawatt to 38 megawatt. Okay. And obviously the transformer rating which I can select is near about 45 MVA, which should be more than this value. So that is obviously 38 divided by 0.85. So it's almost coming to the 45 MVA. Okay. So here the case is clear. We have a 110 kV system which is connected to the grid, and to this 110 kV there is a transformer of 45 MVA is connected, and it is stepping down the voltage from 102 to 11 kV. And on the 11 kV side we have a load connected. So here the load varies from 10 megawatt to 38 megawatt, whereas the voltage fluctuation on the grid is from 12.5 to minus 17.5%. Now the question is how to identify the OLTC range. That's the question here. I hope if we do the OLTC for this example, so probably you will understand this. So now the question is how to identify the OLTC range. Okay. So for that, let me go to the ETAP here. Let me create a small single line diagram for this. So we have a grid, and yes, and you have a transformer. So here, and there is a load connected to this. So here the voltage, the bus voltage is 110 kV, and here it is 11 kV. 11 kV, and the transformer rating is 45 MVA. So 45 MVA. Impedance, I am assuming it as a typical impedance. On the load, I am assuming that the load will vary from 10 megawatt to 38 megawatt. Then how to find the OLTC range? That means to regulate the bus voltage within plus or minus 5%, right? So yes, now here, let me take one grid condition here. So here the rating, the grid voltage. Okay. So instead of that, what we will do is you go to the settings, loading and generation categories, and here you change this generation as, you will get as a maximum grid voltage, and this is minimum grid voltage, and this is normal grid voltage. Okay. Right. Now, so grid voltage, we have to keep two things. One is on the positive side and another is on the negative side. So the maximum grid voltage, the allowed it is of how much? Plus 12.5%. So that is 112.5. And similarly on the negative side, we have to select minus 17.5, right? So that's what I have given here. So this will be 100 minus 17.5. So this gives 82.5. Okay. So the minimum side grid voltage is 82.5 and the normal grid voltage is 100%. Okay. Fine. Next, coming to the lump load here. So here on the lump load, you have the maximum load, minimum load. Of course, we don't have the normal load here. So here normal load is not required. So the maximum load is of 38 megawatt and the minimum load is of 10 megawatt. But what we have to do here is, so here you have to give it in the terms of the percentage. Okay. Here you have to give this in terms of the percentage. So what I am doing is, I am giving this in terms of the percentage. Instead of that, what I am giving is, I am giving it as a 45 MVA. So that is the load. And here I will give the percentage. Okay. Here I will give you the percentage. Suppose if it is constant power load, assume it as a constant power load. Suppose the maximum load is, let's suppose, yeah. So here this is 38.25 megawatt at 85% power factor. So if you give 100%, so it will be 38.25 megawatt. Okay. And for the minimal load, again, here if you give something like, how much we have to give? So 10 megawatts, so you can give some 10% that we will change it. Okay, now for 10% it is 3.825. So if you give something like 30%, it is or some 27%. Yes, it will be something like this, 26% or 27%, something like that. Okay, so for 27%, so the load is 10 megawatt, near about to approximately 10 megawatt. So you have a 45 MVA load and 85% power factor. The load varies from 27% to 100%, so which brings the load variation from 10 megawatt to 38 megawatt. Okay, right. Now, let me do one thing here. So before performing the load flow, we will take the another scenario also. Take the another scenario. So one is like here, you have the normal load, maximum load, and you have, sorry, first let me take the minimum load and the maximum grid voltage here. Okay, so let me copy this. And yes, now take the option as move from dumpster, just ungroup this one. Okay. So here we need to run two different cases. One is with 100% load, that is with 38 megawatt, and another one with the lesser load, that is 10 megawatt. And also we have to run for the different grid voltage also. Okay. Now, so first let me change the load from, see, let me create a points here. So one is your grid voltage is maximum, grid voltage and the load. Okay. So here, if you see here, the grid voltage is maximum, correct? And the load is maximum or minimum. So here I am considering the minimum. Similarly, the grid voltage is maximum, load is also maximum. Next, the grid voltage is minimum, load is minimum. If the grid voltage is minimum and load is maximum, right? Now, out of these four cases, two cases will give you the extreme conditions. And as we discussed yesterday, yesterday we discussed about the 9 cases. Out of 9 cases, only 2 cases will give you the extreme conditions. So if we perform this for the, hello? Yeah. So, but yeah. Yeah. So if you take the grid voltage and the load, so here out of these 4 conditions, 2 conditions will give the 2 extreme conditions, right? So what are those 2 conditions here? One is this condition, that is grid voltage maximum and load minimum. Second is grid voltage minimum and load maximum. Okay. Right. Now, so what we are doing is here we are doing the same cases here. So one is the grid voltage is maximum. So for that, what I am doing is the maximum grid voltage. So select the condition here. Loading. This is the grid voltage is maximum and the load is minimum. Okay, for this condition. So this I am just keeping it aside just to understand. So now run the load flow here. Right. Now if you see here, for the maximum grid voltage and the load is of minimum load, right? 10 megawatt. So for maximum grid voltage and minimum load, your bus voltage is going beyond 5%, right? The allowable limit on the bus voltage on the 11 kV side is plus or minus 5%, right? So what we have to do here, we have to put the tap changer.
Sir, can you zoom it so we can't read it?
Yeah. Right. Now, if you see here, just what I'm doing is I'm putting some random tap. Let's suppose it is from +5 to -5% tap. Let's suppose it will be. Okay. So let's suppose I'm giving, because this gives the positive side tap. So I'm giving the 5% tap and again run the load flow. Now, if you see here, so the bus voltage coming within the allowed limit, still it is more than the 5%. So the next step, what we have to do is we have to give this percentage as 6.25. Normally it will be in terms of the 1.25%. So 6.25. So here now the bus voltage is come well within the prescribed limit. Okay. Clear? So this gives the tap on the maximum side. That means the maximum tap, we have defined it as 6.25. So with the tap of 6.25, we are able to bring this down the voltage, or we are able to regulate the voltage at the 11 kV bus well within the 5%. Okay.
Okay, sir.
Yeah. Now, next the thing is, we have to one second. Yeah. Now the next side is positive side. We have assumed it is as 6.25% is fine. So on the negative side, what we have to do, we have to take the another scenario, that is the minimum grid voltage. Okay. On the negative side, we have to do the generation category should be the minimum grid voltage and the loading category should be the maximum. Okay. So now run the voltage. Okay. Here the bus voltage is 65.59%. So what we have to do, here the tap is 6.25%. So instead of that, let me put minus 10% tap and see how it will be. 82.52, still with minus 10% step also we are not able to maintain. So let me increase it to some 12.5%. It's still 85.51. So if we increase it to minus 20% step, and let's see how it will be. Yes. So with 20% tap, minus 20% tap, we are able to maintain 95.39%. That means well within the limits. Okay. So in this way, we have to define the positive side as well as
Negative, sir.
Okay. So first what we have to do, we have to perform the fixed tap. You have to try to check with the fixed tap. That means on the positive side, you have fixed it as 6.25%, whereas on the negative side, you have fixed it as a minus 25%. Okay.
Okay, sir.
Yeah. Right. So now then next option is, so this is the basically the offload tap changer. Then the next thing is you can use the onload tap changer also for the same. So here I will keep it as a 0. And on the LV side, which bus voltage regulated you want to control. So you want to regulate the bus 10. And we know that the tap range is from
minus 6.2.
Minus 22 plus 6.
Minus 22 plus 6.25.
Yeah, minus 22, 6.25. So minus 22 plus 6.25%. Okay. And click this OK. And if you ask this, so now the came, and here there is an option that is called transformer LTCs. So if you select that and check this, so this ETAP will automatically do that minus 20% tap. Okay. Similarly, if you change this voltage from grid voltage from maximum grid voltage and minimum load here, check this and run this. So automatically with the 6.25% step, here I have not given, right? I have given the range. Or here you can give the range from, let's suppose, tap of 6.25 I have given. So let's suppose give the tap of, I don't know, 10% I have given, for example. Okay. Then run this. So automatically at 10%, you are you are able to bring the voltage well within 100.4%. Because how the tap will work? The tap works with this range, upper band and lower band. So if the voltage is well within the limit, so it will try to adjust the voltage to that value. But the maximum tap, at least that is required, is of 6.25%. So with this 6.25%, we will able to bring down the voltage from 100 and from bring down the voltage from well within the limit of plus or minus 5%, right?
Yes.
Yes, sir.
Yeah.
Sir, this is an extreme tap, upper lower limit and lower limit. How will we set the intermediate taps?
Hmm?
These are the last tap, no? That minus 6 plus 6.25 and last is a 20 minus 20.
Yes.
Positive limit and negative limit. So
Yes.
what about the intermediate taps, sir?
Yeah, intermediate tap, of course, you can do the regulation, right? But here our requirement of this with the tap selection is to maintain this voltage well within plus or minus 5%. So
Yeah,
that's why you have defined the extreme taps.
That's it clear, sir. But
Yeah.
how to set? So we have to give the five number of taps, no, for the benefit.
No, it's not mandatory. Like if you take the case of the station transformers and all, so there you will have 17 taps also.
Okay. So how to set that intermediate taps? This is a upper limit and lower limit. So what about the intermediate taps? We have to. Is there any condition or is there any specific guideline for that?
Oh, no, it's not like a specific guidelines and all. See,
Generally, what about the LV side voltage? We are giving the 2.5% of the each tap
no.
variation.
See,
So that is that might
depends.
not be for the utility. So
Yeah. Here I have taken a typical case, like if you take the case of a 415 volts, so there the voltage allowed ranges are plus or minus 10%. So probably that time you may not need the 6.5%. So there you may be plus or minus 5% tap will be sufficient. Okay. But here in this case, as I have I'm going to regulate the voltage well plus or minus 5%. So I have taken the maximum tap as 6.25%. But yeah, if we want to allow this to voltage variation of plus or minus 10%, so definitely 6.25% is not needed. Probably your means 2.5, yeah, 5% will be sufficient. Like let's see that 5, if it is 5, and see that, wait, this is on, right? Go to the tap here and make this to 0, and here if it is of plus 5%, tap and run this. So now here the bus voltage is 105.5. So probably in this case you may not need 5% also. Let's check with the 2.5%, how it will be. So here 108%. That means still well within the limit of plus or minus 10%. So here 2.5% is also sufficient. So this completely depends upon your the voltage variation that is allowed.
okay, sir. Thank you.
Okay.
Sir,
Right.
sir, I have one doubt. But here we are fixing our upper limit and lower limit, right?
Hmm.
But how we will decide the step size? Because in station transformer or grid substation, normally we have seen 17 steps and each having 1.25 or likewise. But in the case of distribution substations, we are using normally 2.5 likewise step. How we will decide the steps having this much of percentage? That how we will decide.
So that's what I told you. Now, by performing the studies, you will able to know, right? Because ultimately you have to maintain your voltage well within the permissible limits, right? If you would not maintain the limit, then probably you need to, like your transformers, everything will get overloaded and you will operate with a very poor power factor. Okay.
Okay. But for that, we need only the upper limit and lower limit, right?
Yes, obviously, because with that, with those upper and lower limits, you will able to maintain. See, once you decided the upper and lower limits, then in between this, any taps, your voltage of this 11 kV will be well within the permissible limits.
Yes. Within this one, all are within the permissible limit only.
Yes. So that's what yesterday also we discussed. Out of 9 cases, Two cases will give the extreme conditions. So here also we are doing the same. We are trying to find out the extreme conditions. Okay. If the
Okay.
condition gets satisfied in the extreme condition, so obviously in between it will satisfy automatically.
Okay.
Yeah.
Okay. Yes, sir. Continue.
Yeah. So this is about how to select the this one. Okay, how to select the tab changers and all. So any doubts in this? How to select the tab changers and all? OLTC?
Yes.
Right. Yeah, any doubts in this? So with this probably so that's why so now with this we can complete the load flow. So probably our load flow is completed. So there are so many topics in the load flow, but yes, I try to cover the major topics with respect to the load flow. So if you have any doubts,
Hello, sir. Uh,
yeah,
Sir, actually, this OLTC concept is for in order to meet our power requirement at the load terminals, right, sir?
Yeah.
By getting the voltage, by varying the voltages, right?
Yeah.
So, what about this reactive power compensation, like how that concept, sir? Suppose if
See,
reactive
reactive
power.
compensation is different philosophy. Reactive compensation is completely different.
So that is not a part of this load flow, right, sir?
Yeah.
Okay. Okay.
Reactive compensation is also a part of the load flow.
Then how we do that, sir?
See, reactive compensation means when you are like generally this reactive compensation will go for the solar and the RE sources especially, right?
Yeah,
So
yes.
there what you have to do is with the different voltage, grid voltage conditions, how much reactive power you are able to supply on the grid. Okay.
Yes.
Yeah.
Sir, I have one more doubt.
Yeah. So reactive power compensation, like by varying but for the different grid voltage conditions, whether you are able to pump or you are able to maintain that much of reactive power at your interconnection points. So for that, you will do that. Okay. Yeah. Next doubt.
Sir, I have one doubt because in the initial station transformer, you had told me that we are using the LTC for reactive or control. Can you elaborate that point?
Can you come again? Come again.
Because in the initial time for the grid substation, we are using the OLTC in the transformers.
Yes.
You told me that it's to control the reactive power by using, you have explained using PQ curve. Can you elaborate that point a little bit more?
Yeah. See, for the grid substation, it will be something like this. Suppose. Yeah. So 1 second, just 1 second. Here, if you see here, as per our grid code, it will be something like this. Okay. It will be something like this. And here, this is your P curve and this is your Q curve. Okay. Suppose, let's suppose you are declaring your plant capacity as 100 megawatt, for example. Okay. So at 100%, let's suppose this is of 100 megawatt. So at 100 megawatt, at least you need to support 33% of the reactive power here and 33% of the reactive power on the leading side. Okay. 33% of the reactive power on the lagging side and 33% of the reactive power on the leading side. Okay. So for in this, what we will do is for the different grid voltage conditions, we will draw a PQ plot. Like, so suppose grid voltage is, let's suppose 110%, grid voltage is 100%, and grid voltage is 90%. In three conditions, you have to maintain this amount of reactive power. Okay. So for that, what we will do is we will take an equivalent network and we will draw the PQ curve. That means for 100 megawatt, you know this value 33 MVR, and here this is minus 33 MVR. So for different grid voltages, with the help of the inverters, whether you are able to maintain this 33 MVR on the lagging side and 33 MVR on the leading side, that you will validate. If you are not able to meet that requirement, then you have to use some additional reactive power compensation devices, or you may use some additional inverters to meet this reactive power requirement. Okay. But OLTC is completely different. OLTC purpose is to regulate the voltage of the bus, but here it is the support requirement and reactive power requirement support that you are providing at the grid connected station. So both are a little bit different things. Okay.
Okay.
Sir, one more doubt. Suppose we are having a transformer of 40 by 50 MVA.
Hmm.
In this, in that case, how the calculation will be? It will be like this same, or it will be different, sir?
Sorry. Can you come again?
Suppose the transformer is not a single base; it has got a 40 by 50 MVA transformer.
Okay.
So how the calculation will be done?
No, obviously you have to do it for the extreme condition, right? 50 MVA, because the 40 and 50 MVA is of the cooling mechanism. But ideally, you can use the transformer up to 50 MVA also, right? If you have the
Yes.
cooling system. So obviously you have to design your OLTC for the 50 MVA, not for the 40 MVA.
Okay, sir. Sir, can you just do it once again, sir? Just show it once again, sir.
Which one?
The tap selection extreme case.
This is simple. I write one condition is here I am getting to find out the tap for two conditions. One is maximum grid voltage, minimum load, and minimum grid voltage and maximum load. So grid voltage, what I have done, I have selected the maximum grid voltage. In this loading here, I have selected the maximum grid voltage and minimum load. So this gives you the maximum tap. So for that, what I have done, I have simply changed this tap to, let's suppose, 5% and checked it. Check the voltage permissive at this bus. So this is 105.4. But my requirement is I need to bring the voltage within plus or minus 5%. That means less than 105%. So for that, what I have to do, I have to increase the tap of this. So I have changed the tap from 5 to 6.25. Okay. And again run it. So now if you see here, the voltage of this 11 kV bus is well within the limit of plus or minus plus 5%, right? 104.5. So this is less than 105% of this permissible limit. So that's why in that way we have finalized this tap on the positive side. Similarly, on the negative side, which condition you have taken? We have taken the minimum grid voltage and maximum load. So minimum grid voltage and here the maximum load here, and run the load flow. So tap is already 5%. So what I'm doing is I'm bringing the tap to 0. So if there is no tap at the nominal tap, your voltage of this bus is 71.68. So what I have done, I have changed the tap in the negative side to, let's suppose, minus 15%, and I have verified how much it is coming, 88.64. Then I increase the tap further to minus 20%. Okay. Now if you see here, so the voltage is well within the limit of 95.39%.
Okay, sir. Okay, sir.
Okay.
Yes, sir.
This way you can do that. Yes. Yeah. Anything else? So if it is clear, so till now, whatever we have discussed up to the load flow, any doubts if people can ask. From the next week onwards, we will start the short circuit.
Sir, one more doubt for me. For like this, if we have, for example, if I'm having 160 MVA transformer, So like for that also, if I do like this in the ETAP, it will be the same process or it will be the different one.
Same only. It will be the same.
So for example, you know, none of my project I'm having 400 bar 220 kV, 220 kV.
Okay.
So in that also, yeah, along with that, if I'm doing for the both the transformers parallelly, so I can do the same or I have to do for the separately.
You have to do it separately, obviously.
Mm-hmm. Oh, okay, sir.
That depends on
So we
your operating conditions, right?
Okay, sir. So what I think we have the ETAP the free software in that we can able to provide it or not, sir. This one.
Yes, in the ETAP you can get it.
Okay, sir. Why? Because means you are running. Why? Because means sometimes if we are trying it, I am trying from my end, but I cannot. I have some issues. I don't know why it is. So during the next class, or we can call you directly for the help in this case. Regards.
Yeah, I will try.
Okay, sir. Okay, sir. Okay, sir. Thank you.
Mm. Hello, sir.
Sir,
Yes. Yes.
Sir. Hello, sir.
Yeah, please.
Sir, whenever we are using that the solar cell, sir, so why there is also tap changer required, sir? Because
Which
the
one?
solar side have a solar cell, sir, solar project, sir.
Yes.
So why they are need, sir? Because of the solar side have a no load and no issue side for a grid maintenance, sir. Voltage, sir. So
No. See, you in the solar, you can there is an operation called night queue mode. Suppose if your solar plant is connected to a large means a large transmission line, right? So
yes,
when
sir.
there is no solar power, but your solar station will be connected to the grid just to meet the auxiliary power requirement, right?
Yes,
So
sir.
that
Yes, sir.
time your voltage will be quite high because the line is almost unloaded. Due to the Ferranti
Okay.
effect, your end voltage means your receiving end voltage will be high. So to obviously, so if you were receiving end voltage, that means suppose if you say, you assume like this, so this is your solar plant, okay? So
Okay.
this is the long transmission line. So here the bus voltage is high. That means obviously the voltage on the LV side of the transformer will also be high, right? So to regulate the
Okay.
voltage there, you need the OLTC or the OCTC.
Okay, sir.
Yeah.
And sir, OITC only one application for a voltage regulation, sir. Yesterday you are
I
not
told
telling
you,
like
right?
that.
I
Yeah.
told you two applications. One is to regulate the voltage and second is to extract the maximum capability that is available in the generator.
Sir, and another is the you are not telling like the angle between the voltage to control the angular voltage, sir.
So
Yesterday to
that,
you.
see, that is for the reactive power flow management.
Okay, sir. Okay.
Okay.
Okay. Okay, sir. No issue. Okay. Understand.
Sir, regarding the diversity factor you removed.
Yes, there is. Yeah. So here in this, there is one option called the diversity factor. So right now I don't have any immediate example to explain this diversity factor. So let's see this. So if I'm able to manage with this, so let me check with this. Unfortunately, I don't have the example, but yes, if possible, I will try to come with some example in the next class. Okay, for the diversity factor, how the diversity factor varies and how it impact in the system. Okay, that probably I will take some 10-minute session only for the diversity factor. Yes. Yeah.
sir, if I go
Yes.
to the solar plant parallelly connected to the grid, shall I know the reactive power compensation in this class or will be a separate class?
No,
If
that
I
will be
connect the
completely separate. That will be the complete different study.
okay.
Reactive power compensation is a completely different study. That will not with this OLTC and all. That's a completely different study. Okay. Right. So this load flow we are ending, and next means from next session onwards we will go through this short circuit, and after short circuit we will go with the relay coordinations and all. So okay, fine. So because today I was a little bit tired, actually I'm not able to take much time. I'm really sorry for that, but yes, we can finish this load flow session. So almost I tried to cover all the major topics that are required for the load flow. So fine. Yes. So if it is clear, so I will end the session for today.
Time permits for future. Can you please explain that reactive power compensation, sir? Because it is a regular task in my current working task, sir.
Oh.
Not now, sir, but after completion of your
Yes,
complete
yes,
syllabus.
yes, yes,
complete
yes,
syllabus.
yes. But
Thank
generally,
you.
as I told you, one thing, let me tell you. So for reactive power compensation, yes, I cannot say that you cannot do it in ETAP. Yes, you can definitely do it in ETAP, but PSSE and the Dixieland power factory are the perfect softwares for doing the reactive power compensation, where you can adjust the inverters, voltages, everything and all. So, but here a little bit tedious, but yes, you can do it. I will try to explain also. Okay.
Thank you so much.
Great, yeah. Okay, fine. I'm ending the session for today. Okay, so. Right.